Hello there and welcome to PowerPoint number 7 for our Math 60 courses. We're going to talk today about set and set notation. This correlates with section 2.2 in our current textbook. But let's get started. There are many sets of numbers, and sets of numbers can be both finite or infinite, large or very small. And there are a variety of ways of us to express these sets of numbers. Four particularly we're going to talk about today, the first being the roster method. Then we're going to talk about the set builder notation, then the interval notation, and that in conjunction with a number line. So these are the four different ways that we're going to look at expressing sets and getting organized. So let's use the roster method, our first, to list the elements of a set. And let's start with a simple example. The set of all months of the year whose names begin with the letter J. So we go through our months of the year, 12 months, of course. Letter J, there are only three. There's January, June, and July. And so when we put things in roster method, we literally take however many elements. Here there are three different members of this set, January, June, July, and we put them in these brackets or braces. And we separate the different elements or members by commas. So January, June, July, commas between them, and then we put brackets or braces. So this format is what's referred to as the roster method. Let's go through a number of examples so we can practice this. Use the roster method to list the elements of the following sets. We're going to begin with the set of all negative integers greater than or equal to, that's important, equal to -5. And this is what it looks like. Again, equal to -5, make sure that we include -5, and the roster method makes sure that we're just listing all of the members separated by commas and using these braces. Another example, let's look at the set of all negative integers greater than -5. Now this looks very similar to our last one. The difference is it's strictly greater than, so it doesn't include -5. So this would be the same set of four members, -4, -3, -2, -1, and the roster method, we would put them inside these braces. A few more examples of the roster method. The set of all factors of 18. Remember, factors are all numbers that multiply together to equal 18, like 2 times 9. Another way of thinking of it as factors are all numbers that divide evenly into 18. So when we put this in the roster method, it would look like this. 1 times 18, 2 times 9, 3 times 6. These are all the factors of 18. And of course, putting them in braces makes it roster method. The set of all integers between 3 and 9 would look like this: 4, 5, 6, 7, and 8. These are the integers between. Now, strictly between does not include 3, does not include 9. The set of all integers between 3 and 9 inclusive. This word inclusive means you're including both 3 and 9, so it would look like this. So these are all examples of the roster method. Now let's look at one other variation of roster method, and that is what if we had a very large set of numbers where we don't want to list every number, or we have an infinite set of numbers? How could you put that in a roster method? Well, here's an example. List the set of all natural numbers less than 500 in roster form. That's a lot of numbers. Now we don't want to make a roster, brace 1, 2, 3 all the way up to 500. So what we do is we list the beginning enough members of this set to establish a pattern, and then we list the end of the set to show where it terminates, but then in between we use these 3 dots. We call that an ellipsis. An ellipsis, the 3 dots, is used to indicate that the set continues in that given pattern. So let's practice this a little bit. Use the roster method to list the elements of the following sets. The set of even integers. Okay, well there's a lot of those. So we would want to, of course, include 0, 2, 4, 6. But once we have that pattern established, then we would use these 3 dots, the ellipsis, to show that it goes 8, 10, 12 without actually listing them. Now, of course, integers also include the negatives. So you have -2, -4, -6. And again, we use the ellipse to say the pattern continues in that direction forever. So there's an infinite set. Another example, the set of all positive multiples of 10. That would be 10, 20, 30, 40, and of course that continues. So we would use the roster method to list it this way. Again, listing enough members of the set to set the pattern, and then the ellipsis to imply that it continues. Then lastly, the set of all integers between 500 and 600, there's that word again, inclusive. So we're going to include 500 and 600. So we put it in roster method. It looks like this. Beginning with 500, we establish the pattern. We put our ellipsis to say it's everything in between that according to the pattern, and it ends at 600, inclusive. So the roster method can be used to describe some finite small sets, and in some cases it can describe some infinite sets if there's an established pattern, but there are other types of sets that aren't as easy to set a pattern, and so they might require a different notation. Therefore we have this set builder notation, interval notation, and number line. So let's get started with looking at those. Here's another example. Describe the set of all real numbers greater than -5. So real numbers, that's not just the integers, -5, -4, -3, -2, but all of the decimal and fraction values in between that. Could we use roster method and literally be able to describe and list everything that goes in there? I don't think so. So what we're going to do before we launch into the set builder notation, interval notation, and number line, let's talk about numbers, just so as we're throwing these terms around, nobody seems lost a little bit. Whole numbers, when you hear the term and title whole numbers, we're strictly talking about just 0, 1, 2, 3, 4, 5. When we talk about integers, then those are all of those same nice whole numbers, but we also include the negative values in that. -1, -2, -3, together with the whole numbers 0, 1, 2, 3. So those are integers. When we talk about rational numbers can be any number written as a fraction. So we always write it as P over Q, fractions. Now, technically, 2 is a fraction because we can always write it as 2 over 1. 3 is a fraction, 3 over 1. So the integers are all part of this set, rational numbers, but it also includes, of course, what we would envision as your traditional type fractions, 1/3. And of course, 1/3 is not a whole number. So anything that can be written as a fraction where, of course, the denominator, Q, cannot be 0. And of course, that does include the decimals that equivalent to this. So 1/3 is 0.33. Sorry, this is going to get a little messy. And of course it goes 0.33 forever. So we use this repeating bar. So whether you write as a fraction or decimal, it's still considered a rational number. Then we have the irrational numbers, and essentially that's anything that cannot be written in one of these forms. So it's non-terminating, it's non-repeating. Some examples might be pi. Most of us are familiar with that, 3.14, and the decimal keeps going. Square root of 2, square root of 7. Any decimal that does not repeat and does not terminate is an irrational number. Then lastly, our real numbers. Our real numbers are just made up of all the rational numbers, anything written by like a fraction, and all the irrationals, things that can't be written that way. So all of these lumped together, which makes up everything on the number line, we call real numbers. Okay, so there's just kind of a quick review of the different types of numbers we refer to and talk about. So now let's look at the examples of set builder notation along with interval and number line. Describe the set of all real numbers. Again, we know what real numbers are, greater than -5. So here's the notation mathematically I'm sure you're familiar with. X is greater than -5 here. Here's what it would look like in set builder notation. We would write it, again, using braces or these brackets, X, and then this bar here, this vertical bar means such that. So we would read it X such that. And now we're going to describe what values what parameters need to be satisfied. So we'd say it's the set of all x's such that x is greater than -5. This is set builder notation where we would always tell that it's a set of items such that then we would go on and describe the parameters for that set. Now on the number line, x is greater than -5, we would write one of two ways. Of course, you see both arrows go to the right because it's greater than -5. Here's -5. Now, one has an open circle, one has a curved parenthesis. Both of these imply that you go all the way up to -5, but does not include -5. Now, knowing that, if we put it in an interval notation, the interval notation would look like this. And the interval notation is specifically using the rounded parentheses. And then it starts at -5, then there's a comma, and it ends at infinity, because of course these arrows imply that everything up here is greater than -5. So it would go all the way as big as you can imagine, which conceptually would be infinity. And these rounded parentheses imply that it does not include the -5. It goes as close as you can possibly get, but not including it. So we would also use a parenthesis on this side because infinity is not a specific value and you can never equal infinity, so it does not include it. So we'd never use a square bracket to imply that we could. Now let's look at another example. Describe the set of all real numbers less than or equal to 9. So it would look like this: x is less than or equal to 9. Our set builder notation will always be the set of all x's such that, and then we describe the parameter or requirements to be in that set. There's our set builder notation. And then our number line, similar to the first one. Now this case it's less than 9, so we're going to go to the left. The difference here is that when we graph it on a number line, we either enclose the dot at 9 or we use a square bracket at 9. Both of these imply that you are also including the value of 9. When we write this in interval notation, then we want to reflect that, and so we write it this way. And I'll bet you can imagine why we write it this way. First of all, we use a curved parenthesis with the negative infinity being the lower end of our interval, and but it's a curved parenthesis because we can never equal negative infinity, so it doesn't include it. However, we use the square bracket on the right side, so we're implying that all the numbers between negative infinity and 9 are included in the set, including 9. Here's one that does a little of both. The set of all real numbers greater than or equal to, keep your eye out for that, -5, but less than 2. So it would look like this. Here are all our values, x, and they are in between -5 and 2. Now, in between meaning that these values are going to be bigger or greater than the -5, and at the same time less than 2. So they're in between that. One thing you want to notice is, of course, we have less than or equal to, so we make sure the notation reflects that. Now our set builder notation then will include this statement, but it'll say the set of all x's such that, and then we state the parameter that x has to be in between. Little tip here: whenever you have numbers in between two values, a common mistake is that students won't place these inequalities in the same direction. Specifically, these two inequalities always have to be facing the same direction. If you ever had something where it was written this way and then it was written in the opposite direction, well, that's going to be an error or a mistake for sure. So make sure these are pointed the same direction to imply that you're in between these two. Now on a number line, this becomes easy to write because we're including -5 but not including 2. So on the number line, we would just draw a solid bar between -5 and 2 with either an enclosed dot or a square bracket at -5, including, or an open dot or a curved parenthesis at 2, not including. And this is where interval notation really shines, because this allows us to really simply write it quickly and succinctly this way. -5 is the lower boundary of our interval, 2 is the upper thing, so we're implying everything in between, but we use a square bracket here because we include -5. Rounded parenthesis does not include 2. So let's have you practice some of these. If you'd like to pause this, you can try these on your own. Describe the given graph using set builder notation. So here's the graph of the number set we're trying to describe. Which of these set builder notation best fit that? And the answer here is 2. It's the set of all x's that are in between -9 and 7, not including 7, but including -9. These include both, so it's wrong. This includes only 7 but not 9. This one, as you can see, includes the -9, does not include the 7, so this notation is correct. Let's try another one. Describe the given graph using interval notation. And we are given the same graph, so we just talked about that. The difference here is the correct answer is again 2. The difference here is that it's asking for interval notation. So while this is correct, this is set builder notation, and that's not what it's asking for. This is the correct interval notation. -9 lower boundary, 7 upper boundary, does not include 7, but does include -9. That's what's in error here on number 3. So in summary, there are infinite and finite sets of numbers, large and small. Some sets can be listed using the roster method, which means you just literally list what's in them in between the braces. Others can't, the infinite large ones. So we have a set builder notation, and it always has the braces, and it reads the set of x's such that, and then you describe the parameter or requirements. We have interval notation, and the interval notation always has the lower boundary, upper boundary separated by comma, and then the use of either parentheses or brackets is important because it tells us whether it's that endpoint is included in the set or not. And then lastly, of course, we can use a number line, and the number line again gives us the opportunity to say whether 4 is included or isn't. In this case it's not, and it's less than 4. So all 3 of these give the same information in slightly different ways. Hope that helps you on sets.